Welcome to Topcast and to the second part of my series on kind of about a discussion between Sam Harris and Max Tegmark that was had years ago on the Making Sense podcast. In this part of the discussion, we're mainly focused on mathematics and the philosophy of mathematics and how we come to know mathematics. And a lot of what I would say are misconceptions from the mathematician's misconception tend to creep in here. The mathematician's misconception is that the brain, or the mind rather, of a human being, and especially of the mathematician, has privileged access to mathematical certainty or mathematical truth in some way. That the way in which mathematical knowledge is created, or the theorems of mathematics come to be known to mathematicians, is something other than this fallible method of conjecture and refutation. That there is some other way of gaining insight into absolutely necessary truth, or certain truth, or something like that. This is the mathematician's misconception that mathematics doesn't require a physical computation in order for us to come to understand it. But that's just wrong. All knowledge, mathematical, scientific, moral, political, whatever it happens to be, has to be arrived at via a human mind which is running on a computer which is obeying the laws of physics. And the laws of physics mandate that you will have errors now and again. That's simply unavoidable. That's just the way knowledge is generated, via this method of error correction, identifying the errors and then correcting them. And that's what motivates all of knowledge creation, finding some problem or error in the existing theories, or even theorems, and then improving on them. There is no final knowledge. There's no way of tying up with a little bow what we have discovered in any area. There will always be open questions. We're always just at the beginning of infinity, beginning to scratch the surface of our understanding of reality. Now, early on in the discussion, I think you can hear a sense of confusion coming through. One thing I would say is that people struggle with this idea that number, mathematics, the theorems, or whatever you want to call it, these objects of mathematics have an existence, have an independent existence. And when I say that, I just mean that, well, these things, these truths, aren't made of atoms. Material stuff is made of atoms, but if you are committed to being a materialist or a physicalist, and this is the idea that you will only grant existence to things made of atoms, or stuff in the physical world that is made of physical stuff, you kind of get yourself tied up into knots then, because if you're talking about, let's say, the laws of physics, which you might grant exist, they're not made of material stuff. They're not made of particles or anything like that. They're not even made of space or energy. They are the explanations of space and energy. They're the things that control what's going on, in a certain sense. So if you're a physicalist, you're automatically believing in, or you're endorsing the existence of, something that's not made of matter. Or are you? I don't know. Some physicalists maybe deny that the laws of physics are real things as well. You get some strange ideas among people who practice professional philosophy. What I like to say is things like numbers exist. They have independent existence. They exist abstractly. They're not made out of matter. And then people say, abstractly, it sounds like you're a Platonist, that these objects of mathematics have some sort of existence outside of the physical world. But where is this other realm of this Platonic realism? And that's the wrong question. That question actually doesn't make any sense. It makes as much sense to me as asking what I was doing decades before my grandfather was born. I mean, grammatically it's a correct sentence, but it's referring to something that didn't exist, and that doesn't exist, and that couldn't exist, and it just makes no logical sense. It's illogical when you actually try and think through what's going on. It's the same as what was happening before time was created. Now, if you have an explanation of the beginning of time, asking about what happened before time, likewise, doesn't make any sense. Asking what's outside of all of space, likewise, makes no sense. You're asking for an explanation of the spaces outside of space. You're just postulating more space. I would say that the same kind of thing is a mistake when we say, where is this realm of abstract reality? Well, it's not anywhere, it just exists. The physical world consists of space-time and the stuff in it, energy and matter. So that's what the physical world is. And there are places in the physical world, and there are times in the physical world, if you like. But the abstract world, that's not made of space-time. It's not made of energy and matter. It consists of truths, abstractions drawn from that physical world, but they're not part of the physical world. They're not made of that physical world, but we come to understand these abstract things using our minds, which themselves are abstractions. So it's perfectly okay to say something has an existence without being able to place it in time and space. That's perfectly fine. In fact, you kind of get a sense that Sam is almost getting this. At first, he seems to be suggesting that an idea of Platonism, the idea that this abstract reality exists in some way. Now, I'm not really sure exactly. It depends on who you ask, right? When you ask different Platonists what their version of Platonism is, some of them will talk about a physical space of some kind, which, as I say, I think it's a category error. When you start talking about physical spaces of abstract stuff, well, how do you marry these two things together? That doesn't really make any sense. Abstract spaces are different to physical spaces. Sam almost gets there because later on in the conversation, I think we'll get there today, he actually talks about an example that I invoke myself very, very often. And that is the example of what is the next highest prime number? At the moment, we know, you can go to Wikipedia and you can find out what is the highest known prime number, and they'll give you a number, a very, very large number. Now, we happen to know, as a matter of proof, there are infinitely many primes. Now, the next one, yet to be discovered, it exists. It absolutely exists. And the one after that, and the one after that. An infinite number of prime numbers exist. But where? Well, certainly not in the physical world, not made out of any atoms. They haven't been instantiated, represented anywhere in existence yet. But they must exist because we can come to discover them. We're not inventing them. We are discovering these things. People are searching for them, literally searching where? Searching through abstract space, the abstract space of numbers. Computers are working hard, grinding away right now to try and locate in that space, that infinite space, mind you, the next prime number, the next highest prime number that will hold the record until such time as the one after that is discovered, then the one after that, and so on it goes. This continual discovering of this landscape out there. Now, we exist in physical reality and we are used to physical reality. This is not to say that there can't be these other landscapes that we can come to understand more and more. Sam invokes one himself, the moral landscape. And I would say, that's also quite right. We can imagine a moral landscape of well-being, by whatever definition. I also like to invoke Jaron Lanier's concept of a disciplined dualist here. I like to think of myself as a disciplined dualist, that we can say that these abstract things exist, but not much more than that. We can come to have a better and better understanding of this abstract reality, but not much more than that. And asking questions that are about the location in time and space, in other words, where in physical space is the abstract stuff, is just a category error. Now, some people are upset about that. But again, it's making the mistake of presuming that there is only one kind of thing, the stuff made out of matter that exists in space-time. But that's wrong. That's just wrong. There are such things as emergent stuff which are beyond merely matter, beyond merely atoms. There's something else going on. We know they exist because they are invoked when we explain the world using our best explanations. And what do we say? A thing exists insofar as it features in our best explanations, and not otherwise. And when we say it exists, we mean we know it exists. What else could we mean? And sometimes things that we think exist turn out not to exist, like the force of gravity and phlogiston and élan vital. These things, scientifically in the history, were thought to exist, and then we found they didn't exist. We had a better theory that ruled those things out and instead postulated other stuff, space-time and oxygen and information and evolution by natural selection. That kind of stuff exists now. We know it exists now. Do we know absolutely for sure that it will never be overturned, any of that stuff? No. But that's not what saying something exists means. This is the distinction between ontology, what ultimately, absolutely as a matter of final truth exists in some way, shape or form, to which we don't have access, and epistemology, our knowledge of physical reality. And we have access to physical reality and to abstract reality and all the other domains in which we might consider our knowledge applicable, ways in which we can come to understand reality broadly. We have access to that via epistemology. but always approximately and always in a way that leaves more and more questions for us to continue to answer and make progress. And this distinction between ontology and mathematics, what really truly exists, and our knowledge of what really truly exists, this distinction here is also where the mathematician's misconception comes in. And one of my favourite lines from The Fabric of Reality sums up this entire notion. And that line is, necessary truth is merely the subject matter of mathematics. Necessary truth is not the reward we get for doing mathematics. So it's the distinction between, and I've said this before on Talkcast, between whatever the fundamental constituents of matter really, really are, and our knowledge of the fundamental constituents of matter at any given time. Now, the history of that just shows that we continue to find smaller and smaller stuff. Now, it used to be thought that atoms were the smallest thing, and then we found out that there were subatomic stuff, protons, neutrons, and electrons. And then we found out, well, even the protons and neutrons are made of these things called quarks. And now people are saying, well, maybe the quarks are made out of strings. And so our knowledge of the ultimate constituents of matter at any particular time is imperfect. It leaves open questions. We do not know the final ultimate constituents of matter. Particle physics isn't about finding the ultimate constituents of matter. Instead, it's about finding our best explanation of what we know the constituents of matter are at any given time. At any given time, we know the constituents of matter, but not perfectly, not finally. That's not what know means. That's not what knowledge is. It's not about a final completed science. It's about explaining what we know at any given time. So too with mathematics. But this is very poorly understood, in particular by mathematicians, and hence the mathematician's misconception that David Deutsch talks about. It is mistaking our knowledge of the necessary truths of mathematics with the necessary truths themselves. If you could grok the necessary truths in and of themselves, that would be inerrant. But how would you get this inerrant knowledge? How would you escape from the fallibility of the human mind? How would you escape from the fact that whatever your mind is doing as a matter of physics is a physical process? Whenever it's doing mathematics or performing a calculation or a computation, that is the action of neurons made of atoms, obeying laws of physics, the quantum laws of physics. And the quantum laws of physics introduce error into the system, uncertainty all the time. That's just a law of physics, and laws of physics are primary. They rule over everything, including brains, including what brains do. They constrain how perfect our knowledge of anything can be, and that includes mathematics. But the mathematician's misconception is, no, we can escape that when we're doing mathematics. When we're doing mathematics, we can actually grasp ultimate truth. And this is simply wrong. Among other things, mathematics produces theorems via a method of proof. And the method of proof must begin somewhere, with the axioms. But you don't know the axioms are true. Of course, some people will say, how could they be otherwise? Well, I would just implore anyone listening to this who wonders about how could it be otherwise to go to my discussion with Naval, there at the Naval podcast, where I talk about precisely this thing, and I invoke the idea of people thinking, how could it be otherwise that two dots drawn on a piece of paper would have a unique line going through them? How could it possibly be otherwise? How could Euclidean geometry possibly be otherwise? How could we have a geometry different to this? That's the history of mathematics, of common sense, of logic, of people even thinking they've found absolutely secure foundations, absolutely unarguable. It could not possibly be otherwise. This is logically proved. Well, even those things can be overturned. The history of mathematics, philosophy, logic tells us this. So this is our topic for today. And as I say, mainly it's me talking. Already it's been about 15 minutes of just me talking. But let me bring you a little bit of what Sam has to say and then some of what Max has to say on precisely this topic of the relationship between mathematics and the physical world. And I'm going to pick it up where Sam is talking about that most famous of papers, Eugene Wigner's, on the unreasonable effectiveness of mathematics and the physical sciences.
I want to linger on this question of about the primacy of mathematics and the strange utility of mathematics. At one point in your book, you cite the off-cited paper by Wigner, who I think he wrote in the 60s about, right, in a paper entitled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." And this is something that many scientists have remarked on, there seems to be a kind of mysterious property of these abstract structures and chains of reasoning where mathematics seems uniquely useful for describing the physical world and making predictions about things that you would never anticipate, but for the fact that the mathematics is suggesting that something should be so. And
That's right.
This has lured many scientists into essentially mysticism, or at the very least philosophical Platonism, and sometimes even religion, positing mathematical structure that exists, or even pure mathematical concepts like numbers that exist in some almost Platonic state beyond the human mind. And I'm wondering if you share some of that mathematical idealism, and I just wanted to get your reaction to an idea that I believe I got from a cognitive scientist who lived I think he died in the 40s, maybe the 50s, Kenneth Craik, who published a book in 1943 where I think just in passing, this anticipates Wigner by about 20 years, but in passing he tried to resolve this mystery about the utility of mathematics, and he simply speculated that there must be some isomorphism between brain processes that represent the physical world and processes in the world that are represented, and that this might account for the utility of mathematical concepts. I think he more or less asked, is it really so surprising that certain patterns of brain activity that are in fact what mathematical concepts are at the level of the human brain can be mapped onto the world, that there's some kind of sameness of structure or homology there? Does that go any direction toward resolving this mystery for you, or do you think it exceeds that?
So there's a few things there I want to pick up on. One is that there seems to be this, and Sam does this rather frequently, conflating brain with mind. And then saying something like, well, mathematics at the level of the brain just is a certain pattern of neural firings. No, that's a wrong level of analysis. The mathematics is an abstract kind of thing. It is our knowledge of mathematics is an understanding. And an understanding is not just a pattern of neural firings. For one thing, one day, in principle, it's possible to take the mind out of the brain so there will be no neurons whatsoever, and instead you'll be instantiated in silicon. A mind can be instantiated in silicon. And then what do we say? The mathematics is identical to the transistors switching on and off? I would still say no. It's the wrong level of analysis. It's like saying that the events of history are nothing but the movement of atoms. That's wrong. Yes, movement of atoms were happening, but if you want to understand, not merely predict, as we like to say, then you have to distinguish between these things. Neural firings are neural firings. And there are all sorts of neural firings. Neural firings happen when you move your leg. Neural firings happen when you digest your dinner. Neural firings happen when you think of artistic things and when you think of mathematical things and when you think of scientific things. But if the fact that it's all neural firings doesn't mean that those things all reduce to neural firings. That would make them all identical. Namely, they'd all just be neural firings. But they're not just neural firings. There's something special about particular patterns of neural firings, and it's the patterns, the abstractions, how those abstractions are represented in the neurons, which is the really interesting thing, because you can instantiate mathematical truth, mathematical explanations, just like you can with any knowledge, in different physical forms. You can write it down on pieces of paper as ink. Does that mean the mathematics is identical to the scribbles of ink on the paper? No. You can say out loud Pythagoras' theorem. Does that make Pythagoras' theorem identical to the sound waves? No. It has its independent existence. It's there in the squiggles when you write it on the piece of paper. It's there in these sound waves when you speak the theorem. It's there when you think it in neural firings. It's represented in all these different ways. And from those different ways, we abstract out the common thing. That common thing being Pythagoras' theorem, which has this independent existence, independent of each of these things. In what sense is it independent? Because it's not identical to any one of those things. Where does it exist then? Well, it exists in each of those forms, but not identical to those forms. But where? Where is the actual Pythagorean theorem? That's the wrong question. It doesn't exist in space. It just exists as an abstraction. as an abstraction. And we only have access to that abstraction once we've come to an understanding of it. The same is true of the next highest prime number. The next highest prime number, we will be able to write down on paper if we like. There would presumably be many thousands of pieces of paper we could write it down on. Someone could say it out loud. That would be ridiculous and probably take their lifetime or something. We can put it as pixels on a screen. There's all these different ways of representing this number. And all these different representations, they have one thing in common. They all represent the one thing, the abstraction, which is that prime number. And the other thing there is this mystery about exactly why it is that mathematics should be useful in describing the physical world. I think this is over-egged sometimes, but here's an answer. Here's an in to that kind of thing. Firstly, all the laws of physics are computable. They're not incomputable. The functions are all computable, which is really interesting. They're these analytical functions. And so because the laws of physics as we know them, we can use them to make predictions in the world, well then, that gives them a mathematical structure, that they are computable. The interesting thing about Feynman, you listen to Richard Feynman talk about this, and he thinks that it doesn't necessarily need to be the case that in the future, laws of physics necessarily have to have this mathematical character in the way we think of mathematics today, which is there's a lecture out there on the difference between mathematics and physics. He talks about this. It's quite a famous lecture. You can find it on YouTube. And just towards the end of that lecture, he actually makes some remarks about how he thinks the final law of physics or something like that, theory of everything, whatever, might not even be written in mathematics, or at least the mathematics as we would think of it today.
I must say that there is possible, and I've often made the hypothesis that physics ultimately will not require a mathematical statement, that the machinery ultimately will be revealed, just a prejudice like one of these other prejudices. It always bothers me that in spite of all this local business, what goes on in a tiny, no matter how tiny a region of space, and no matter how tiny a region of time, according to the laws as we understand them today, takes a computing machine an infinite number of logical operations to figure out. Now, how can all that be going on in that tiny space? Why should it take an infinite amount of logic to figure out what one stinky tiny bit of space-time is going to do? And so I made the hypothesis often that the laws are going to turn out to be, in the end, simple like the checkerboard, and that all the complexity is from size. But that is of the same nature as the other speculations that other people make. It says, I like it, you don't like it. It's not good to be too prejudiced about the thing.
It's really curious, maybe kind of like we think about constructor theory. Now, maybe there will be a formalism of constructor theory in terms of sophisticated mathematical apparatus. Perhaps, indeed, there will be. But Feynman is sort of hinting at, ultimate, greater, grander, deeper theories might not need to have this same kind of mathematical character. But the tradition in physics, of course, is that we tend in the direction of more sophisticated mathematics. And so now we're at string theory, where the mathematics is exceedingly complex and people struggle to understand it. And to some extent, many physicists are saying, they're not seemingly making any progress by the measure of generating testable predictions. And this is why, a whole bunch of them turn around and say, well, it doesn't matter. That doesn't matter. We're still doing science. Well, yeah, but testable predictions allows you to do things, not just like test the theory against rivals, but also generate stuff like technology. So actually make practical benefits for humanity. Not to say that, mathematics and string theory couldn't possibly have any benefits to humanity. Of course it could, but problem solving requires solving physical problems. Now, there is this problem with unifying general theory of relativity and quantum theory. Yeah, and so string theory is an attempt to do that, but the attempt's been going on for many decades now. And out of that, well, where's the testable prediction? We don't have one. What is the new piece of technology that a company can latch onto and to actually make a profit out? We don't have any. This is a bit of an issue, and it's one of the motivations for something like constructor theory, a new approach, something different that makes some testable predictions that might actually lead towards certain kinds of technology. Who knows? We're still at the beginnings here. Okay, string theory's had its few decades. Let's give constructor theory a few decades, equal time. So that's one thing. The other issue of why it is that mathematics should be so effective in the physical sciences, well, Sam kind of gets at it there, and I use the term self-similarity, and David Deutsch uses in The Fabric of Reality this term self-similarity, and we get a great hint of this in his lectures that he's given, his TED lectures that he's given. This idea that the human mind has this capacity to generate models and explanations within itself that are of the rest of physical reality. So you have this kind of one-to-one correspondence between explanations, claims about reality, and the reality itself. And so this is the whole idea of quasars, David invokes quasars and the discussion of quasars, that here's this object on the other side of the universe, obeying the extreme limits of the laws of physics as we understand them. Stars being swallowed whole by these black holes, ripped apart and generating these huge jets that, if they're directed in our direction, we can detect as quasars. Now, that physics, as David says, is so unlike the physics of the human brain, it's just almost unimaginable. And so go to his TED Talks to hear more about that from his perspective. But the magnificent thing is that our understanding of quasars comes to resemble what's really going on in quasars with increasing fidelity over time. The one structure inside the mind, the model of the quasar, comes to more faithfully represent the real physical thing out there in reality over time. That's the really cool thing. And that's kind of what understanding is. That's what understanding is. So let's hear what Max Tegmark has to say about all of this.
Yeah, that's an interesting argument, the argument that our brain adapts to the world, has a world model inside of the brain.
Our brain is just clearly part of the world, and so there are processes in the world, and there are processes in the world that have by virtue of what brains are, have a sameness of fit and kind of a mapping.
So I agree with the first part of the argument and disagree with the second part. I agree that it's natural that there will be things in the brain that are very similar to what's happening in the world, precisely because the brain has evolved to have a good world model. But I disagree that this fully answers the whole question, because the claim that he made there, that you mentioned, that brain processes of certain kinds is effectively what mathematics is, that's something that most mathematicians I know would violently disagree with, that math has something to do with brain processes at all. They think of math rather as structures which have nothing to do with the brain.
Hold on, let's just pull the brakes there, though, because clearly your experience of doing math, your grasp of mathematical concepts or not, the moment something makes sense or you persist in your confusion, your memory of the multiplication table, your ability to do basic algebra and everything on up, all of that is, in every instance of its being realized, as a state of your brain. Or you're not disputing that.
Of course, absolutely. I'm just quibbling about how what mathematics is. What's your definition of mathematics?
So they're both talking past each other, I would say here, and they're both talking past the most parsimonious way of just sorting out this confusion. And the confusion is the distinction between the subject matter and our knowledge of the subject matter, ontology and epistemology. The real existence of mathematical structures, mathematical objects, things like numbers, and our knowledge of those things. Now, our knowledge of those things is going on, or the creation of the knowledge of those things is going on inside of our minds. Absolutely. That's where the creation is taking place. That's what makes human beings, people, so unique, so special in the entire universe, that we can do this process of create explanatory knowledge. But it's an imperfect process. It's a process of conjecturing, guessing about the reality that's out there. And one of the realities that's out there is mathematical reality. The reality of necessary truths, of absolutely certain perfect number. But we can't grasp absolute perfection. We can only guess at it. We guess at it. We fumble our way through by error correcting. This is the remarkable thing. Now, it's whatever the thing is that exists, by the way. The thing that exists might be matter, the material world. There's an M for you. It could be mathematics. We come to understand the truths of mathematics better, but we're guessing at that. We're guessing at the material world. We're guessing at moral truth as well. Sam talks about the moral landscape, and we can come to understand that moral landscape ever better. What about meditation? There's another one. This meditation, this process of meditation is a process of coming to understand the mind. Yet another M. Coming to understand the mind ever better. Coming to understand your own mind and your problems and your difficulties and whatever else, and the action of thoughts as thoughts. But imperfectly, by the way. Just because you are there in your first person meditating doesn't mean that you have a privileged best understanding of what the heck's going on. Now, certainly it can help, but sometimes you also need to discuss with someone else because they can have better insight into exactly what you're thinking and why. That's a curious thing, right, about ourselves. We tend to think we have this high opinion of ourselves. We go, well, I'm the one with my thoughts, so I understand my thoughts really well. Well, do you? Do you really? You have a lot of thoughts, It's very hard to kind of keep track of everything you're thinking and why you're thinking it and which thoughts you're thinking over and over again. And we make mistakes all the time. I can tell you one thing. When I make these podcasts and I think I'm saying something really clearly and I think I've spoken just exactly the way I want to speak, I go back and I edit. And I've said exactly the wrong word. I think I've said the word, let's say, mathematics. And in fact, I've said the word morality. How ridiculous. And so I have to edit stuff and change my mind. But if you had asked me immediately after having made the sentence, I would have said something like, oh no, mathematics is a domain of necessary truths. And I would have insisted that this is what I really thought I said. And then you play back the tape and I've actually said morality is the set of necessary truths or something like that. I've made a mistake. I can be totally wrong about the contents of my own mind just a second ago. And I think we can be systematically wrong about our own minds as well, by the way. We can just continually tell ourselves we've got the right idea. And in fact, we've got the wrong idea. We're just not thinking clearly. And this is one reason for talking to friends and talking to other people and talking to counsellors and talking to wise older people and trying to come to a better understanding of your own ideas, what you think are your own ideas. Okay, that's a little bit off topic, but what I'm saying here is that everyone understands seemingly this distinction, but when we get into the realm of mathematics, it becomes some area of confusion. And what Sam and Max would benefit from is simply recognizing this distinction, that the mathematicians, again, the mathematicians' misconception, they think they've got access to this final ultimate truth, and that what's going on inside of their brains is the mathematics. It is the set of necessary truths. Now, you've come to an understanding of the necessary truths, but it's going to contain error and misconceptions. That we can always come to a deeper understanding of these things, a deeper understanding. Now, when I say that we can have errors and misconceptions in our knowledge, it doesn't mean that for any particular claim, like, let's say 1 + 1 = 2. People like to bring this sort of thing up, say, how could that possibly be wrong? How could you possibly have an error about that? Well, when I say error, I just mean that you don't have the deepest possible understanding of it. You think you know what 1 + 1 = 2 means. I'm not saying that I know there's something wrong about that claim. Can I doubt the veracity of that claim? I can doubt it. I can doubt that you have a complete understanding of what that really entails. For one thing among many, it was a surprise to me at university learning that you could actually do this thing that proves 1 + 1 = 2, and it takes you about an A4 page of handwritten argumentation from the axioms using Peano's axioms and reaching the conclusion that 1 + 1 = 2. Okay, that requires, there's a method of proof there. So that is it. Once you've done that, you have a deeper understanding, in a sense, of what 1 + 1 = 2 means. Now, what is 1? What is 2? And by the way, like David Deutsch says, what does equals mean? Because it can't mean exactly the same as. After all, just write down 1 + 1 = 2 and notice on the left-hand side, you've got this symbol 1 and you've got this symbol plus and you've got this symbol 1 again. Well, that's not exactly the same as the symbol you've got on the right-hand side, which just is the numeral 2. So these two things are not exactly the same. So equals can't mean that. So there's all sorts of ways we can approach what the difference is between an absolutely necessary truth, which is the subject matter of mathematics, and our understanding of these things, which is where the confusion is, I would say, a little bit between what Sam is saying, what Max is saying, what they're both saying, and they're not quite coming to what I think is a clear distinction, and what other mathematicians, I would say, have on this point. We come to imperfectly understand mathematics. We refine that understanding over time, and all of our knowledge of mathematics is generated by our brains, which is running on minds which are obeying laws of physics, which introduce errors as a matter of physical law. Okay, let's keep going and listening to a little bit more from Max.
Absolutely. I'm just quibbling about how what mathematics is. What's your definition of mathematics? And I think it's interesting to take a step back and ask, what do mathematicians today generally define math as? Because if you go ask people on the street, like my mom, for example, they will often view math as just a bag of tricks for manipulating numbers, or maybe as a sadistic form of torture invented by school teachers to ruin our self-confidence. Whereas mathematicians, instead, they talk about mathematical structures and studying their properties. I have a colleague here at MIT, for example, who has spent 10 years of his life studying this mathematical structure called E8. Never mind what it is exactly, but he has a poster of it. He's on the wall of his office, David Vaughan. And if I went and suggested to him that thing on his wall is just something he made up somehow, that he invented, he would be very offended. He feels he discovered it, that it was out there, and he discovered that it was out there and mapped out its properties in exactly the same way that we discovered the planet Neptune rather than invented the planet Neptune, and then went out to study its properties. Similarly, if you look at something more familiar than E8, you just look at the counting numbers, 1, 2, 3, 4, 5, etc. The fact that 2 plus 2 is 4 and 4 plus 2 is 6, most mathematicians would argue that this structure, this mathematical structure that we call the numbers, is not the structure that we invented properties of, but rather that we discovered the properties of. In different cultures, this has been discovered multiple times independently. In each culture, people invented rather than discovered a different language for describing it. In English, you say 1, 2, 3, 4, 5. In Swedish, the language I grew up with, you say 1, 2, 3, 4, 5. But you can, if you use the Swedish-English dictionary and translate between the two, you see that these are two equivalent descriptions of exactly the same structure. And similarly, we invent symbols. What symbol you use to write the number 2 and 3 is actually different in the US versus in India today or in the Roman Empire, right? But again, once you have your dictionaries there, you see that there's still only one structure that we discover, and then we invent languages.
Yeah.
Right. To just drive this home with one better example, Plato, right? He was really fascinated about these very regular geometric shapes.
I couldn't agree more. Perfect. Exactly right. That's what I would like to be able to say as well, just as clearly. I endorse everything there. I think he's got it exactly right. What we would also add, he goes on to use the example of Plato. Plato had the Platonic solids. He wasn't free to just invent more Platonic solids once he'd discovered the ones that existed. In other words, mathematics kicks back. It has this independent reality that once you discover some part of it, whether it's E8 or the Platonic solids or just the natural numbers, they have this autonomous set of properties that you come to understand over time by making more and more discoveries, generating more knowledge about that particular thing. So that's exactly right. And we know it exists. We know this stuff exists by, as David Deutsch talks about in The Fabric of Reality, that these things kick back. That's Dr. Johnson's criterion. What does kick back mean? Well, it does something kind of unpredictable that you prod it a little bit and it gives you back some kind of information about itself. So in the case of, just the normal natural counting numbers, well, it gives you back this weird, unexpected kind of thing of the prime numbers. The distribution of prime numbers is kind of weird. When the next one is going to crop up is kind of weird. What the highest one at any given point and then the next highest one. These things are out there to be discovered. So you start off with this simple set of assumptions, the axioms of simple arithmetic, and you end up with the natural numbers and you end up with the prime numbers of infinite kind of complexity in a certain way. And they exist, these things exist, by the measure that they feature in our best explanations of reality. Our explanations of reality include, the capacity to count stuff, to calculate, to compute, and so then we end up with the revealed richness of things like prime numbers, among other things. Okay, so we'll go on and listen to what Sam has to say about this.
What is the highest prime number above the current one we know? Well, clearly there's an answer to that question.
You mean the lowest prime number above all the ones we know?
Oh, yes. Oh, sorry. Yes. The next prime number.
Yeah, yeah.
That number will be discovered rather than invented. And to invent it would be to invent it perfectly within the constraints of its being, in fact, the next prime number. So it's not wrong to call that a pure discovery, more or less analogous, as you said, to finding Neptune when you didn't know it existed, or going to the continent of Africa. It's Africa is there whether you've been there or not.
Right.
So I agree with that, but it still seems true to say that every instance of these operations being performed, every instance of mathematical insight, every prime number being thought about or located or having its, every one of those moments has been a moment of a brain doing its mathematical thing.
Right.
So I'm just
or a computer sometimes.
Yes.
Because we have an increasingly large number of proofs now done by machines.
Right.
And discovery is also sometimes.
We're still talking about physical systems that can play this game of discovery in this mathematical space that we are talking about. This fundamental mystery is that why should mathematics be so useful for describing the physical world and for making predictions about blank spaces on the map? And
exactly.
I'm kind of stumbling into this conversation because I'm not a mathematician, I'm not a mathematical philosopher, and so I'm sort of shooting from the hip here with you, but I just wanted to get a sense of whether this could remove some of the mystery. If in fact you have certain physical processes in brains and computers and other intelligent systems, wherever they are, that can mirror this landscape of potential discovery, if that does sort of remove what otherwise seems a little spooky and platonic and represents a challenge for mapping, abstract, idealized concepts onto a physical universe?
Yeah, that's a great question. And the answer you're going to get to that question will depend dramatically on who you ask. There are very, very smart and respectable people who come down all across the very broad spectrum of views on this. And in my book, I chose to not, say this is how it is, but rather to explore the whole spectrum of opinions. So some people will say, if you ask them about this mystery, there is no mystery. Math is sometimes useful in nature, sometimes it's not. That's it. There's nothing mysterious about it. Go away. And then if you go a little bit more towards the Platonic side, you'll find a lot of people saying things like, it seems like a lot of things in our universe are very accurately approximated by math, and that's great, but they're still not perfectly described by math. And then you have some very, very optimistic physicists like Einstein and a lot of string theorists who think that there actually is some math that we haven't maybe discovered yet that doesn't just approximate our physical world, but describes it exactly and is a perfect description of it. And then finally, the most extreme position on the other side, which I explore at length in the book, and that's the one that I'm personally guessing on, it is that not only is our world described by mathematics, but it is mathematics in the sense that the two are really the same. So you talked about how in the physical world we discover new entities and then we invent language to describe them. Similarly, in mathematics, we discover new entities like new prime numbers, the Platonic solids, and we invent names for them. Maybe this mathematical reality and the physical reality are actually one and the same. And the reason why, when you first hear that, and it sounds completely Looney Tunes, of course. You look, it's equivalent to saying that the physical world doesn't just have some mathematical properties, but that it has only mathematical properties. And that sounds really dumb if you look at your wife or your child or whatever, and you're like, this doesn't look like a bunch of numbers. But to me, as a physicist, when I look at them, of course, when I met Annika, your wife, for the first time, of course, she has all these properties that don't strike me as mathematical.
Don't tell me you were noticing my wife's mathematical properties.
But at the same time, as a physicist, I couldn't help notice that your wife was made entirely out of quarks and electrons. And what property does an electron actually have? Well, it has the property -1, 1/2, 1, and so on. And we've made up nerdy names for these properties, we physicists, such as electric charge, spin, and lepton number. But the electron doesn't care what language we invent to describe these numbers. The properties are just these numbers, just mathematical properties. And
so all is number. This is the Pythagorean idea. That essentially, the true reality of the physical world we inhabit is actually reducible to mathematics in some way. But I just think, well, this is metaphysics. This is a preferred metaphysical claim. Now, saying there that the electron has these properties described by numbers, -1, 1, and so on and so forth, that is saying that the object is the properties. But I just think that's wrong. I think that we can always come to a deeper understanding of these things. What is an electron, after all? Well, physicists have refined their understanding of this thing over time. It began as a particle, then they said a wave. Now we think of this idea of fungible instances of the electron, this particle. I don't think we're going to get to the ultimate final answer as to what an electron is. Now, as for saying that ultimately an electron reduces to nothing but the mathematics of an electron, well, again, it's a metaphysical claim. And people have preferred metaphysics, but I don't know why they in fact have preferred metaphysics. And why physicists want to say, well, I think it's just to sell books. Maybe that's what it comes down to. It's like that you make a strong claim that everything's reducible to mathematics, and you sell more books because people want to argue against you. Now, I don't have a strong opinion on this. I just think that it's one of these claims where there's little point arguing about it because there's no way of testing, at the moment, the truth of this matter. But one thing I would say is that it just doesn't comport with what I understand about the rest of physical reality, which is that we come to a deeper and deeper understanding of it over time. That if, for example, string theory describes what fundamental particles are, so-called fundamental particles, they wouldn't be fundamental anymore, the strings would be the fundamental things, then we would have a deeper understanding of the electron as a certain vibration of a string. But then you would say, well, what's the string made out of? Ultimately, what is that? And people of the future, physicists of the future, I would imagine, would come down in some way, shape or form in saying, well, actually the strings are made out of this other stuff. And so on it goes. Because, like we say here, we're at the beginning of infinity. We're at the beginning of our understanding of things. But Max is kind of postulating, and many physicists do this, what the ultimate end game is. So they think there's an end game. They think the end of science is coming. Or they think the end of physics is coming. Narrowly, the theoretical physicists have this fixation on the final completed physics. Unify a few more things, unify the forces, and then one or two steps beyond that, you get to the final ultimate end point. I just don't think that's going to work. I think there's going to always be open questions. There's always going to be a question as to why. Why? And if you're saying that this abstract stuff, which we call mathematics, the knowledge of mathematics itself is abstract, the mathematical things themselves are abstractions for all the reasons I talked about earlier. If you're saying that's what physics ultimately is, then physical spaces, in some sense, reduce to abstract spaces. And then the question about where this abstract space is actually is a meaningful question. Here it is. We're occupying an abstract, not a physical space anymore. But then we're presented with the same list of questions. You're still going to have the question about the origins of the universe is still going to come up. You're still going to have the question about dark energy. You're still going to have questions about what the fate of the universe was. Are there other logically possible universes that we can access in some way? Let me pick it up just for a few more minutes with Max, and then I'll say a few more things and we'll tidy it up for today.
And if you take seriously that everything in both your life and in the world is made of these elementary particles that have only mathematical properties, then you can ask, what about the space itself then that these particles are in? What properties does space have? Well, it has the property 3, for starters, the number of dimensions, which again is just a number. Einstein discovered it also has some more properties called curvature and topology, but they're mathematical too. And if both space itself and all the stuff in space have only mathematical properties, then it starts to sound a little bit less ridiculous, the idea that maybe everything is completely mathematical and we're actually part of this enormous mathematical object.
Okay, so we'll end it there for today. But what I would just say about that is I think it's the same mistake that was being made earlier. I think it's just confusing knowledge of something, mathematical knowledge of physical structures, with the structures themselves. That's all. That descriptions, our use of these mathematical labels for certain properties are not identical to the properties. I think that's just wrong. Now, saying that the electron and the quark differ only in these properties is just to say our way of describing differences between these things involves numbers. So, for example, you say something like an electron has a charge of -1, whereas certain quarks have a charge of +1/3. So, but does that explain what charge is? That charge is just literally numbers? Well, I don't think so, because if you're saying that, then you're also saying, well, the mass of the electron is what it is, and the mass of the quark is what it is, but that doesn't explain what mass is. It doesn't explain what charge is either, and how charges behave. That part of the explanation is obscured from you if you're just going to say, well, they're nothing but these numbers. Then explain why there should be attraction between things or not, or repulsion between things or not. Now, Feynman gave this great explanation as to why, for example, electrons, when brought close together, tend to repel one another because they're emitting photons towards each other. Well, that's an explanation, but it's not reducible just to the number properties. You need natural language in order to come to an understanding of this stuff, to explain what the numbers mean. And the numbers are just being invoked as part of the explanation. But then go that step further and say, well, the explanation, these parts of the explanation are not only just explaining what's going on here, it is what's going on here as a matter of final fact, that the electron is just a set of numbers. It's confusing knowledge of with the thing in itself. The thing in itself, you don't have a perfect understanding of. We should know now that we don't have a perfect understanding of particle physics. For one thing, particle physics is part of quantum theory, and quantum theory doesn't quite mesh with general relativity. So we know we've got progress yet to make, problems yet to solve. Okay, but that's where I think we'll leave it today. We'll move on from mathematics next time to some other part of the discussion. I don't want to go through the entire discussion. I think you get a sense now of the way in which I'm approaching this. But again, it is nice to see how I would suggest that just picking up the books Fabric of Reality and the Beginning of Infinity do give you this, as I like to talk about, this coherent worldview. And so you're able to spot misconceptions and spot errors and kind of feel, in a sense, a little bit more clear in your thinking about certain things, that where others tend to encounter confusions and trip-ups, you may not. This is certainly not to say we have all the answers. Absolutely not. It's just that when you have a way of meshing together the philosophy, epistemology, morality, mathematics, physics, computation, and all of these other things, it allows you to error correct more easily and more easily move in these subjects, even if you're not necessarily a top-notch expert. And I don't regard myself as a top-notch expert in physics. I'm a layperson. I'm not a top-notch expert in Popperian epistemology, I would say. I'm not a top-notch expert in astronomy or anything else, but I tend to be able to spot the errors in thinking, because, this thing conflicts with that thing, which we know is the case because of our best existing explanation. And this thing conflicts with that thing, and that can't be right because, again, conflicts with our best known explanation. So when people start deviating from what is known as a matter of our best explanation, our best current understanding, and when you know that the view they're espousing has already been refuted in some way by some other thinkers, then it's an interesting way to sort of look at some of these discussions. But still fascinating, still very, very interesting. And not saying it's altogether wrong, certainly not. A lot of what Max has said here today and a lot of what Sam has said here today, I completely agree with. It's just really interesting, those areas where we part ways, so to speak, because of a different, deeper philosophy and especially understanding of epistemology. But until next time, bye-bye.
Girl,